Hello there, and welcome to the Sleepy Space Channel. The Neptune you learned as a child is quietly being taken apart. The deep blue world at the edge of the Sun's family, the frozen and featureless twin we were all shown, has turned out to be wrong in almost every part. Its famous color was never really there. Its family of moons appears to be the survivors of an old catastrophe. Its light glows in the wrong place. Its outer air is cooling for reasons no one can name, and it may not even be the kind of planet we always called it. Tonight, we move slowly through everything the newest discoveries have revealed about the real Neptune. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to hold on to. There is nothing out there at the cold edge of the Sun's family that asks for your worry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day drift quietly away. Let's begin. There is a planet at the very edge of the Sun's family that almost no one has truly seen. It is the eighth and outermost of the major worlds, the last full stop at the end of the long line of planets. For most of the time we have known about it, it has been described in a single breath as a cold and distant blue world, the quiet twin of the planet just inside it. That description is calm and tidy and easy to remember. It is also, in almost every part, quietly wrong. The planet is Neptune, and the strange thing about it is how little of our familiar picture has survived close inspection. We believed we knew its color. We believed we understood its family of moons. We believed we knew what it was made of, and why it earned the name we gave it. In the last stretch of years, sharper eyes turned toward that far blue point have unsettled nearly all of it. The planet we thought we knew is being slowly replaced by a stranger one, and the replacement is still underway. To begin, it helps to simply sit with where Neptune is. It orbits the Sun at roughly 30 times the distance that separates the Sun from the Earth. That number is easy to say and hard to feel. From Neptune, the Sun is no longer a warm disk in the sky. It is a single brilliant point, brighter than any other star, but far too small to warm anything. The light that reaches Neptune is only a tiny fraction of the light that falls on us. It is a world lit by a distant lamp, held in a permanent, gentle dusk. At that distance, everything about the planet moves slowly. Neptune takes so long to travel once around the Sun that a single Neptunian year is well over a century of our years. Since the planet was first found, it has completed only a couple of laps of its enormous orbit. If you could stand on one of its moons and watch, the Sun would seem almost fixed, creeping along a path that takes lifetimes to close. There is a deep patience built into the place, a slowness that belongs to the outer dark. And yet Neptune itself is not small. It is about 4 times the width of the Earth, and roughly 17 times its mass. If it hung where the moon hangs, it would be an immense blue-green wall across the sky. But it does not hang nearby. It sits so far away that from here it is never more than a faint speck, far too dim to see with the unaided eye. You could look at exactly the right part of the sky on the clearest night of your life and never know it was there. This hiddenness is part of what makes Neptune feel so different from the other planets. The worlds closer in have always been companions to us, bright and obvious, tracked and named since long before anyone understood what they were. They rise and set, they wander among the stars, they are part of the shared sky that every generation has known. Neptune has never been part of that shared sky. It has always required instruments and effort and knowing exactly where to look. It is a planet that belongs to the telescope rather than to the naked eye, a world we have to seek out rather than simply notice. And when we do seek it out, what we find is a globe of deep atmosphere with no solid surface to stand on. If you could somehow descend into Neptune, you would never strike ground. You would only sink through air that grows steadily thicker, warmer and heavier, until the very notion of gas and liquid loses its meaning and you are simply within the body of the planet. There is no shoreline, no mountain, no plain, nothing to set a foot upon. The whole world is a gradual thickening of matter, from the thin, cold air at the top to the crushing, dense material far below. That absence of a surface is one reason the planet is so hard to picture. We are used to worlds with faces, with landscapes we can imagine walking across. Neptune offers no such thing. What it offers instead is depth, layer upon layer of atmosphere shading into interior, a world defined not by its surface, but by its interior gradient. To understand Neptune is to think in terms of layers and depths rather than places, and that alone makes it a stranger subject than the rocky worlds we know best. It is a giant that distance has reduced to a whisper. It helps, sometimes, to build a small model of that distance in the mind. Imagine the sun shrunk down to the size of a single lamp on a table. On that scale, the Earth would be a grain of sand a few paces away, warmed and lit. Neptune would be another, smaller grain, but you would have to walk a long way across the room to find it, far out past everything else, at the cold edge of the lamp's reach. And the light, which crosses from the Earth to the Sun in about 8 minutes, would take some 4 hours to travel out to that distant grain. Neptune is so far that its sunlight is measured not in minutes but in hours. That distance shapes the character of the whole world. The outer reaches of the planetary system are a place of cold and quiet, where the sun's warmth has thinned almost to nothing and its light has faded to a point. Neptune lives permanently in that thin light, wrapped in an atmosphere far colder than anything on Earth. The upper reaches of its air are among the coldest naturally occurring places in the Sun's family. And yet the planet is not still. Beneath that frigid surface, Neptune is one of the windiest worlds we know, driven by some of the fastest sustained winds ever measured on any planet, winds that race around the world at speeds that would be violent beyond imagining if you could stand within them. This is one of the first quiet contradictions of Neptune. It is a world so far from the sun that it receives almost no warmth, and by every simple expectation, it should be calm, sluggish, and settled. Instead, it is restless, banded with fast-moving clouds, marked from time to time by great dark storms that rise in its atmosphere, linger, and then fade away again. Something inside the planet keeps it active, some source of energy that does not come from the distant sun. A world at the cold edge of everything has no business being so alive, and yet it is. The storms themselves come and go in ways we are still learning to read. Dark spots, enormous rotating systems larger across than whole continents, appear in the atmosphere, drift for a time, and then dissolve, only for new ones to form elsewhere. They are not permanent features but passing weather, the visible signs of a deep and moving atmosphere. Bright clouds sometimes gather above them, high hazes catching what little light there is. For a planet once imagined as a smooth, unchanging ball, Neptune turns out to have a sky that never quite holds still. Even the simple matter of counting Neptune's moons has kept changing. For a long time, the tally stood at a handful, then grew as better instruments picked out fainter and smaller companions. The count now stands at 16, and the 2 newest of them were spotted only very recently, small dark worlds so dim that they had escaped every earlier search. That we are still finding moons around Neptune this late in our exploration of the Sun's family says a great deal about how faint and far the planet is. Even its retinue of moons is not fully mapped. There may be smaller ones still, waiting in the dark for a sharper look. Each of these discoveries is a reminder that Neptune remains, in a real sense, unfinished business. Most of the inner worlds have been mapped, orbited, landed upon, studied for generations. Neptune has not. It sits far enough out and faint enough that our knowledge of it is still growing in the most basic ways, still adding moons to the count and corrections to the picture. It is one of the last places in the Sun's family where the fundamentals are still being settled, where a careful look can still turn up something genuinely new. That is part of what makes the planet such a rewarding subject for a slow evening's thought. It is not a closed book, fully read and shelved. It is a world still coming into focus, still surprising the people who study it, still holding more than we have managed to see. And nearly every one of those surprises traces back to the same root cause, the enormous distance that has kept Neptune at the very edge of what we can perceive. The planet turns quickly, even so. Despite its size, Neptune spins once in only about 16 hours, so a day there is shorter than a day on Earth. Beneath a deep atmosphere of hydrogen and helium, carrying a small but important trace of a gas called methane, lies an interior of heavier material that we are only beginning to understand. Around the planet drift faint, dark rings, and a family of moons that now numbers 16, 2 of them found only very recently. For a long time, that was more or less the whole story, and it was a story told at arm's length. Almost everything we knew came from faint light, gathered across an enormous gulf, and from one brief visit by a single passing spacecraft, long ago. When your entire portrait of a world is built from so little, the portrait can be confident and still be mistaken. That is exactly what happened with Neptune, and it is why so much has changed so quickly now that we are finally looking harder. So set aside for a while the deep blue marble from the old textbooks. The real Neptune is paler and stranger and far more active than that image ever suggested. Its moons carry the memory of a catastrophe. Its light appears in the wrong place. Its outer air is cooling for reasons no one can name. And on the inside, it may not be the kind of planet we always called it. Tonight, we move slowly through all of it, one quiet discovery at a time. The place to start is the beginning, with the most unusual fact of all about this world. Neptune was not stumbled upon by someone sweeping the sky with a telescope. It was found, first, with mathematics, in the dark, before any eye had ever knowingly rested upon it. To understand why the planet has always been so hard to know, it helps to understand how strangely it was found. Every other planet visible to us was, in a sense, simply there. The bright wandering lights that move against the fixed stars were known to every ancient sky watcher. Even the 2 nearest giants beyond the naked eye were found by the ordinary act of looking through a telescope and noticing something new. Neptune alone was different. Neptune was predicted before it was seen. Its existence was worked out on paper, its place in the sky calculated, and only afterward was a telescope turned to the spot to confirm that the world was truly there. The trail that led to it began with the planet just inside Neptune's orbit, the next ice giant sunward. Astronomers had been tracking that inner world carefully, plotting its slow path around the Sun. And the path, when measured closely, was subtly wrong. The planet did not move quite as the known forces said it should. It drifted, very slightly, ahead of its predicted place at some times, and behind at others. The discrepancy was tiny, but it was real, and it would not go away. Something was pulling on that planet. The gravity of the Sun and of the known giant worlds could account for most of its motion, but not all. A small, stubborn remainder was left over, a gentle tug from an unseen direction. There are only so many things that can tug on a planet, and after the known causes were subtracted, one possibility remained. There had to be another world, farther out, whose gravity was quietly reshaping the orbit of its neighbor. This is where the mathematics becomes something close to beautiful. Rather than search the sky blindly, it was possible to treat the small errors in the inner planet's motion as clues, and to ask a precise question. Where would an unseen planet have to be, and how massive would it have to be to pull its neighbor exactly this way and no other? The problem was difficult, but it had an answer. The wandering of one world could be turned, by careful reasoning, into the predicted address of another. The calculation pointed to a particular patch of sky. When a telescope was finally aimed at that patch, Neptune was there, within about a single degree of the predicted spot, close enough to be recognized on the first careful night of searching. A planet that no one had ever knowingly seen had been located, first, by the pull of its gravity on a distant neighbor. The unseen had been made visible by arithmetic. It is worth pausing on how remarkable that is. Gravity reaches silently across enormous distances, and it leaves traces in the motions of everything it touches. By reading those traces with enough care, it became possible to know that a world existed, and roughly where, before a single ray of its reflected light had been knowingly noticed. The planet announced itself not by shining, but by pulling. It was known by its effect before it was known by its face. There is a longer lesson folded into that discovery, one that runs through the whole of how we study the distant planets. Gravity does not act only in one direction. If Neptune could tug on its inner neighbor and betray its own existence, then it too was being tugged upon by the sun and by every other world. The planets are bound together in an immense slow conversation of gravity, each one pulling gently on all the others, each orbit subtly shaped by the presence of the rest. To read one planet carefully is, in a sense, to read the whole system, because none of them moves entirely alone. The particular pull that revealed Neptune was maddeningly small. The deviation in the inner planet's path amounted to only the faintest wandering, a drift so slight that it took years of patient measurement to establish that it was real at all. It would have been easy to dismiss such a tiny error as a mistake in the observations or as some flaw in the instruments. Instead, it was taken seriously, treated as a genuine signal rather than noise, and followed all the way to its source. That willingness to trust a small, stubborn discrepancy is what made the discovery possible. It is worth remembering, too, that the calculation was not perfect. The predicted planet was found close to where the mathematics said it should be, but the fuller details of its orbit and its distance did not match every early expectation exactly. The prediction was good enough to point a telescope at the right patch of sky, which was a triumph, but Neptune, once found, proved to be its own world, not quite the one the equations had sketched. Even in the moment of its discovery, the planet was already gently correcting the story we told about it, a habit it has never lost. There is a quiet irony in how the planet was found as well. The method that revealed Neptune, reading the small gravitational disturbances of a known world to infer an unknown one, is the very same method that has since been turned outward, again and again, in the search for still more distant things. The same logic that pointed to Neptune has been used to look for other hidden bodies at the edge of the Sun's family, worlds that may or may not be there, whose faint pulls, if they exist, would betray them just as Neptune's pull once betrayed it. Neptune was the first great success of that way of thinking, the proof that the unseen could be reasoned into view. It is a way of knowing the universe that feels almost like listening rather than looking. Instead of waiting to see a thing directly, you attend to its effects, to the subtle ways it disturbs everything around it, and from those disturbances you build a picture of what must be there. Much of modern astronomy works this way, inferring the presence of things too faint or too hidden to see, from the marks they leave on what we can see. Neptune stands near the beginning of that tradition, a world whose gravity spoke for it before its light ever did. And so the planet's discovery is not only a story about Neptune, it is a story about a whole way of coming to know the cosmos, patient, indirect, and quietly powerful. It reminds us that the sky is not simply a collection of visible things, but a web of influences in which even the unseen leaves its trace. Neptune was the first planet to be caught by that web of reasoning, pulled into knowledge by the faint tug it laid upon its neighbor. And the discovery changed something in how we saw the whole system. Before it, the planets were simply the ones that were there, the lights that had always been known. Afterward, it was clear that the system might hold more than met the eye, that there could be worlds waiting in the dark to be reasoned into view. Neptune was proof that the sky was not a finished catalogue, but an open question, and that patient measurement could still turn up new worlds where none had been seen. It marked the moment the outer system became a place to be explored rather than merely observed. Yet the very thing that made the discovery so impressive, the great distance and faintness of the planet, also guaranteed that knowing it would be slow work. A world you can only reason your way toward is a world that gives up its details grudgingly. Neptune had been found, but it had hardly been seen, and the gap between those two things would stretch across a very long time. But this triumphant beginning set the tone for everything that came after. Neptune has always been a planet studied at the very limit of what our instruments can manage. It was inferred before it was seen, and even once it was seen, it remained a faint and difficult target. The same distance that made its discovery such a feat also made it stubbornly hard to study in any detail. A world found by calculation tends to keep some of its secrets in the domain of calculation for a very long time. And so the manner of its finding is really the first chapter in the story of its mystery. Neptune is far enough away that, for most of our history with it, we have had to guess more than we could observe. We reasoned our way to its existence, and then we reasoned our way toward its nature, filling the gaps in thin evidence with reasonable assumptions. Some of those assumptions held. Many of them, we now know, did not. To see why the picture stayed uncertain for so long, we have to look at the simple, stubborn problem of distance and light. The deepest reason Neptune has been so hard to understand is almost embarrassingly simple. It is very far away, and it is dim. A large planet, yes, but so distant that even our finest telescopes have struggled to see it as much more than a small, soft disk. For most of the time we have known it, our entire picture of Neptune was assembled from faint light, patient inference, and a single close encounter that lasted only days. Consider what distance does to light. The amount of sunlight that reaches Neptune is small to begin with, only a thin trickle compared to the flood that falls on the inner worlds. Of that trickle, only a portion is reflected back toward us, and that reflected light then has to cross the same immense gulf again to reach our eyes. By the time it arrives, it is faint, and it comes from a target that appears tiny in the sky. Gathering enough of it to see fine detail is a genuine challenge. Our own atmosphere makes the task harder still. The air above any ground-based telescope is always shifting, and that shimmer smears the light of distant objects into a soft blur. For a planet as small and faint in our sky as Neptune, that blur can erase exactly the details we most want to see. The planet's true face was, for a long time, hidden not behind clouds of its own, but behind the restless motion of the air right above our heads. There is a way to picture the problem that makes it feel very concrete. Imagine trying to read the fine print on a coin resting at the bottom of a swimming pool, while the surface of the water ripples and shifts in the sunlight. The coin is there, and its details are real, but the moving water scatters and bends the light so that the writing dissolves into a shimmer. For a ground-based telescope, the whole atmosphere is that rippling water, and Neptune is a very small, very faint coin at the bottom of an enormous pool. No matter how large the telescope, the shimmer sets a limit on what can be seen. Lifting our instruments above the atmosphere changed this, but only for the fortunate few telescopes that made the journey. From above the air, the shimmer vanishes, and a distant world can be seen far more steadily. Even then, Neptune remains a small target, and time on such rare instruments is precious and shared among countless demands. The planet has had to compete for attention with the entire rest of the universe, and it does not always win. Long stretches pass in which no one is looking closely at Neptune at all. The single spacecraft that visited did so at the end of a long grand tour of the outer worlds, a journey that carried it past one giant planet after another before it finally reached the last of them. By the time it arrived at Neptune, it had already traveled for many years across the width of the planetary system. It had one chance, one pass, to gather everything it could as the planet and its moons swept by. What it captured in those few days transformed our understanding overnight, turning Neptune from a point of light into a world with weather, rings, and moons. But then it was gone, continuing outward, and it has never been replaced. That is worth sitting with. Nearly everything we deeply know about Neptune, in the intimate way that only a close visit can provide, comes from that one encounter. Every measurement of its magnetic field, every close portrait of its largest moon, every count of its rings from nearby, traces back to those few days. In all the years since, no craft has returned. Our knowledge of the planet rests, to a surprising degree, on a single afternoon's visit to a world it took years to reach. It is worth appreciating just how much that one visit accomplished, precisely because it stood so alone. In the span of a few days, a single passing craft transformed Neptune from a smudge of light into a detailed world. It revealed the great winds and the dark storms of the atmosphere. It confirmed and mapped the faint rings. It discovered several small moons that had never been seen before. It made the first close study of the planet's magnetic field and of its largest moon. Almost every intimate fact we hold about Neptune can be traced, in one way or another, to that brief encounter. It was one of the most productive afternoons in the history of exploration. But an afternoon, however productive, is still only an afternoon. A single pass captures a single moment, and a planet is not a single moment. Its storms come and go. Its atmosphere shifts. Its seasons turn across more than a century. To catch a world once, in passing, is to see a single frame of a very long film, and then to spend decades trying to reconstruct the whole story from that one frame, aided only by faint glimpses from far away. It is remarkable that we have learned as much as we have. It is also clear how much must still be missing. This is the deep reason the recent discoveries have so often overturned the old picture, rather than merely refining it. When your foundation is one brief visit and a scattering of distant observations, there is enormous room for a closer look to reveal something new. Each time our instruments have improved, Neptune has rewarded them with a surprise, not because the planet is changing so much, but because we were seeing it so incompletely all along. The world was always this strange. We are only now becoming able to notice. Some of the most striking recent corrections did not even require new observations. They came from looking again, more carefully, at data we already had. The reprocessing of the planet's color is the clearest example. The images that revealed the true, pale Neptune were, in part, the very same images that had shown it as deep blue for decades, handled again with better methods and better judgment. The information had been sitting in the archive all along. It simply had not yet been read correctly. A fresh, careful look at old data was enough to overturn one of the planet's most famous features. This is a quiet but important truth about how understanding grows. We tend to imagine discovery as a matter of new instruments and new expeditions, of going somewhere we have never been and seeing something we have never seen. Often it is. But sometimes discovery means returning to what we already have and reading it with more care, more skill, and fewer assumptions. The data does not change. We change in what we are able to draw from it. And a world can be quietly transformed in our understanding without a single new photograph being taken. Neptune, more than most worlds, has rewarded this kind of patient re-examination. Because so much of what we know comes from that one brief visit and a handful of distant observations, there is enormous value in mining that limited record ever more deeply. Each new technique applied to the old data has the power to reveal something that was always there, but never noticed. The planet's archive is small, but it is far from exhausted, and it keeps yielding surprises to those willing to look again. So the story of learning Neptune is not only a story of reaching farther, it is also a story of looking harder at what we already hold and of the humility to admit that our confident old readings might have been wrong. The pale true color, drawn from images we had possessed for years, is a gentle monument to that humility. It reminds us that the universe is often trying to tell us something we have not yet learned to hear. The newer discoveries, then, have come almost entirely from a distance, wrung out of faint light by ever more sensitive instruments and ever more careful analysis. And this is precisely why they have so often overturned the old picture, rather than merely refining it. When your understanding rests on thin evidence and one brief visit, there is a great deal of room for a sharper look to reveal that you were wrong. Neptune has offered exactly that, again and again, rewarding each new effort to see it clearly with a fresh surprise. Only one spacecraft has ever traveled all the way to Neptune, and it did not stay. It swept past the planet in a brief encounter, gathered what it could in a matter of days, and then continued on into the dark beyond. That single flyby remains, even now, the source of a great deal of what we know. It is an extraordinary record, but it is also a snapshot, one moment in the life of a world that changes over years and decades. A snapshot can be sharp and still be misleading if you mistake the single moment for the whole. Everything learned since that encounter has come from a distance. It has come from telescopes above the atmosphere, from careful reprocessing of old images, and from a new generation of instruments sensitive to infrared light, the warm glow that lies just beyond what our eyes can see. Each improvement in our ability to look has tended to do something telling. It has not merely sharpened the existing picture. Again and again, it has changed the picture, revealing that what we thought we knew rested on foundations thinner than we realized. This is the quiet key to the whole story of Neptune. Because the planet has been seen so rarely, and so faintly, our long-held image of it was always more fragile than it appeared. Confidence is easy when there is little evidence to contradict you. The deep blue, featureless, frozen twin of its neighbor was a perfectly reasonable guess, given how little we could actually make out. It simply was not what the planet is. As soon as sharper eyes were turned toward that far blue point, the reasonable guesses began to give way. The changes did not come as a single dramatic overturning. They came as a series of gentle corrections, each one adjusting some piece of the familiar portrait, until the sum of them amounted to a different world. And the first of those corrections touched something so basic that it is almost startling to reconsider. It touched the color of the planet itself. For decades, if you had asked anyone to picture Neptune, they would have imagined a deep and vivid blue. That blue was on every diagram and in every mind. It was the one thing everyone knew about the planet. And it turns out that the famous blue of Neptune was, in large part, something we did to the picture, rather than something the planet truly does. To see how that happened, we have to look closely at the most iconic images ever taken of this world. Neptune's fame rests more than anything on its color. It became known as the deep blue planet, a sapphire marble hanging in the dark, its blue so rich and saturated that it seemed to belong to no other world. That single striking shade did more to fix Neptune in the public imagination than any fact about its size or its winds. And that shade, it turns out, was never quite real. The most famous images of Neptune came from that single spacecraft flyby, the one brief close encounter we have ever had. The raw images it returned were carefully processed here on Earth, and in that processing, the blue was strongly enhanced. This was not done to deceive anyone. The contrast was pushed deliberately to draw out faint bands and features in the atmosphere that would otherwise have been almost invisible. Boosting the blue made subtle structure easier to study. It also made the planet look far more intensely blue than it actually is. Those enhanced images were the ones that spread. They appeared in textbooks, in encyclopedias, in poster after poster and article after article, until the exaggerated blue simply became the accepted color of Neptune. A whole planet's public face was set by pictures that had been tuned for a scientific purpose, and the tuning was quietly forgotten. Generation after generation grew up knowing, with perfect confidence, that Neptune was a deep and vivid blue. When researchers went back to the original data much later and reprocessed it carefully, balancing it against modern observations of the planet, a different Neptune emerged. The real color is far gentler. It is a soft, pale, greenish blue, not the deep sapphire of the famous pictures. And most surprising of all, in its true color, Neptune looks remarkably similar to the planet just inside it, its supposed twin. The two worlds are far closer in appearance than the old images ever suggested. The reason both worlds are pale comes down to their atmospheres. Both of these outer giants owe their color to that trace of methane in their air. Methane has a quiet habit. It absorbs red light, drinking in the warmer end of the sunlight that reaches it, and leaving the reflected light looking blue-green. So both planets take on a similar cool tint, painted by the same chemistry for the same reason. There is a further layer to it, a layer of haze. High in the atmospheres of both worlds sits a fine veil of haze, and that veil whitens and softens the color we see. On the neighboring planet, this haze is thicker and more sluggish, and it makes that world look paler and a little more washed out. On Neptune, the haze appears to be somewhat thinner, so the underlying blue-green comes through a touch more strongly. That is the whole of the difference. Neptune is slightly more vivid than its neighbor, but only slightly. The dramatic gap between a deep blue world and a pale one was never there. It is worth thinking about why the enhanced blue took hold so completely, because the reason is very human. A deep, vivid blue is simply more striking than a soft, pale one. It photographs beautifully, it stands out on a page, and it gives the planet a strong and memorable identity. The pale, true color, by contrast, is gentle and easy to overlook. Given the choice between a dramatic image and a subtle one, the dramatic image will always travel further. And so the boosted blue spread not through any intent to mislead, but simply because it was the more arresting picture, and arresting pictures are the ones people remember. There is a broader caution folded into this small story. So much of what we know about distant worlds comes to us not as raw experience, but as processed images, pictures that have been adjusted, enhanced, and interpreted before they ever reach our eyes. This is entirely necessary. The raw data from a spacecraft or a telescope is often faint, strange, and hard to read, and it must be handled with care before it means anything at all. But every choice made in that handling shapes what we end up seeing. The color we assign to a planet, the contrast we choose, the features we bring out, all of it carries a fingerprint of human decisions. Most of the time, those decisions are made carefully and well, and the resulting images are honest guides to what is really there. But the case of Neptune's color is a gentle reminder that an image is always, in part, an interpretation. It shows us not just the world, but the world as we chose to render it. And when a particular rendering becomes iconic, it can quietly harden into fact until almost everyone believes it, and almost no one remembers that a choice was ever made. Correcting the color, then, was more than a small technical fix. It was a reminder to hold even our most confident images of distant worlds a little loosely. If the single most famous fact about Neptune could be, in large part, an artifact of processing, then it is worth asking what other confident pictures might soften under a closer look. The true, pale Neptune is a humbler image than the vivid blue marble, but it is a truer one, and there is a quiet value in preferring the truer picture, even when it is less dramatic. There is also something worth noticing in how similar the two outer giants turn out to be. For a long time, the deep blue of one and the paler shade of the other seemed to set them apart, to make them two distinct worlds with two distinct characters. The corrected color brings them back together. Seen truly, they are close kin, two pale blue-green globes painted by the same chemistry, distinguished only by subtle differences in their hazes. The family resemblance was there all along, hidden behind an image that had been tuned to emphasize a difference that barely exists. That resemblance turns out to run deeper than color, as we will see when we look inside these worlds. But even at the level of appearance, it is a gentle correction worth making. The two outermost giants are not a vivid one and a dull one. They are a matched pair of soft blue-green worlds at the edge of the sun's family, more alike than the famous pictures ever let on. To see them side by side in their true colors is to see two siblings, not two strangers. And there is a lesson in this that reaches beyond Neptune. It is a reminder that what we think we see is always shaped, in part, by how the seeing was done. The universe reaches us through instruments and images, through choices about contrast and color and emphasis, and those choices leave their mark. To look at the cosmos wisely is to remember that, and to hold our most vivid images with a little humility. Neptune's corrected color is a small case of a large truth, that seeing clearly sometimes means letting go of a beautiful picture in favor of a plainer one. And once you accept that the planet is not the vivid blue jewel of the old images, the way opens to seeing how much else about it is unlike the tidy story. The color was only the surface. The next surprise reaches back billions of years into the very origin of the planet's family of moons. It is a small thing in one sense. A color is only a color. But there is something quietly humbling in it. The single most famous fact about Neptune, the one thing nearly everyone believed they knew, was partly an artifact of how we handled a picture. If we could be so confidently mistaken about something as simple and visible as the planet's color, it invites a gentle question about what else in the tidy old portrait might not survive a closer look. As it happens, a great deal does not survive. The color was only the first correction. The next reaches far deeper into the planet's history, into the strange and broken family of moons that circle it, and into a catastrophe that appears to have reshaped the entire system long ago. For while most planets keep their moons in neat and orderly arrangements, Neptune does not. Neptune's moons are a puzzle, and the solution to that puzzle is quietly dramatic. Most large planets keep tidy families of moons. The moons form alongside their planet, out of the same disk of material, and they settle into neat, nearly circular paths, all orbiting in the same direction, close to the plane of the planet's equator. It is an orderly arrangement, the sign of a calm shared birth. When you look at the moon systems of the other giants, you see this order written plainly across them. Neptune's system does not look like that at all. Its moons are scattered onto tilted and stretched orbits, some of them running in directions that make no sense for a family born together. The arrangement is irregular and a little chaotic, and for a long time that untidiness was simply noted as a curiosity. Now it is understood as evidence. Neptune's moons are not a record of a quiet birth. They are the aftermath of something violent, and the largest moon holds the clearest clue. That largest moon is a world in its own right, large and cold and geologically alive, with its own thin atmosphere and its own frozen plains. And it does something that no other large moon in the Sun's family does. It orbits backward. It circles Neptune in the opposite direction to the planet's own spin, on a path steeply tilted from the equator. Large moons that form alongside their planet do not orbit backward. That single fact tells us this moon was not born here. A backward, tilted orbit is the signature of capture. This moon almost certainly formed somewhere else entirely, out among the icy bodies of the great cold belt beyond Neptune, the same distant population that includes the most famous of the dwarf planets. It was a free-roaming world of its own, until it wandered too close to Neptune and was seized by the planet's gravity, pulled into orbit and held there ever since. It is less a child of Neptune than a prisoner, taken from the outer dark. The capture of such a large body would not have been gentle. When a massive moon is dropped into a planet's system on a backward tilted path, it becomes a wrecking force. Its orbit would have crossed and recrossed the paths of whatever moons Neptune already had. Over time, its gravity would have flung those original moons about, sent them onto crossing orbits, and driven them into collisions with one another. A system that had been orderly for a very long time would have been thrown into slow, grinding chaos. To feel the strangeness of a backward orbiting moon, it helps to remember how moons usually come to be. When a giant planet forms, it gathers around itself a disk of gas and dust, a miniature echo of the disk from which the planets themselves formed around the Sun. Out of that spinning disk, moons condense, and because they are born from a single rotating cloud, they all inherit its motion. They orbit in the same direction, in the same plane, in neat and nearly circular paths. This is why the moon systems of the other giants look so orderly. They are the tidy children of a single spinning birth. A moon that orbits backward cannot have been born that way. Nothing in that gentle process of formation would produce a large world running against the grain. The only way to get such a moon is to bring it in from outside, to take a body that formed elsewhere, on its own, and capture it into orbit. And capture is a rare and difficult thing. A passing body will usually either fall straight in or swing past and escape again. To be caught into a stable orbit requires a special set of circumstances, some way of shedding just enough energy at just the right moment. That Neptune managed to capture so large a world tells us its history included at least one genuinely unusual event. The captured moon we see today is enormous, one of the larger moons in the entire Sun's family, a world with a frozen surface, a thin atmosphere, and signs of activity that suggest it is far from dead inside. It is a remarkable place in its own right, and one day it may deserve a long, slow evening of its own. But for the story of Neptune's broken family, what matters most is its arrival. A world that size, dropped into the system on a backward tilted path, is not a quiet neighbor. It is a gravitational bull, loosed in the delicate china shop of the original moons. As that great intruder settled into its new orbit, it would have swept through the region where the planet's first moons circled. Its gravity would have stirred their once calm paths into ellipses, tilting and stretching them until they began to cross one another. Moons that had kept safely to their own lanes for ages would in time have found themselves on colliding courses. And in the slow motion of orbital mechanics, over long spans of time, crossing orbits mean collisions, and collisions mean destruction. Even the great intruder itself did not escape unchanged. Over the immense reaches of time, the same gravity that binds it to Neptune has been slowly, gently reshaping its orbit, drawing it inexorably closer to the planet. In the far distant future, so far off that the number of years loses all meaning, that slow spiral may bring the Moon close enough for Neptune's tides to tear it apart, scattering it into a bright new set of rings. The capture that once destroyed a family of moons may, in the end, destroy the captor too, and give Neptune a spectacular ring system long after we are gone. The violence in Neptune's system is not only in the past. It is a slow story still unfolding, on a clock so immense that its hands seem not to move at all. The faint rings of Neptune fit into this story in a quiet way. Compared to the bright, broad rings of the ringed giant farther in, Neptune's rings are dim and sparse, thin bands of dark material that were hard to detect and are easy to overlook. Within them are curious denser stretches, clumps and arcs where the ring material gathers more thickly rather than spreading evenly all the way around. These uneven arcs are themselves something of a puzzle, held in place, it seems, by the delicate gravitational shepherding of small nearby moons. They are the sort of feature you would expect from a system that has been disturbed and rearranged, rather than one that formed in smooth calm. If the rings are indeed made partly from the debris of destroyed moons, then they are a kind of memorial, the scattered remains of worlds that no longer exist, spread into faint circles around the planet. When we look at Neptune's dim rings, we may be looking at the dust of its original family, ground down and laid out in thin bands, still circling the world that lost them. It is a gentle thought that the wreckage of a catastrophe can become something delicate and enduring, a soft ring of memory around a distant planet. And the small moons that remain, shepherding those arcs and circling in their various orbits, are a mixed and motley company. Some may be survivors of the original family, like the one on its strange, stretched orbit. Some may have formed later, gathered from the debris of the disruption itself. Some of the tiniest and most recently discovered may be fragments only lately noticed, small, dark worlds that had escaped our attention until the sharpest modern eyes were turned their way. Together they make up a system that is less a tidy family than a gathering of survivors, newcomers and remnants, all circling a planet whose past was anything but peaceful. The result appears to have been the destruction of most of Neptune's original family of moons. The worlds that had circled the planet since its formation were scattered, shattered, and in many cases ground to pieces or driven down into the planet itself. It is a striking thing to picture, an entire family of moons undone by the arrival of a single outsider. Some who study it have taken to describing the event, informally, as a kind of moon apocalypse, a wiping clean of what came before. The debris from that destruction did not simply vanish. Some of it may survive today as the faint, dark rings that circle Neptune, the crushed remains of moons spread into thin bands. Some of it may have long ago rained down into the atmosphere and been swallowed. Either way, the tidy first family was largely erased, and what we see now is a system rebuilt from the wreckage, a mixture of survivors, newcomers, and the ground-up dust of worlds that no longer exist. This reframes everything about Neptune's moons. They are not a peaceful archive of the planet's birth. They are the scene after a disruption, a record of violence rather than calm. And within that record, there is one small moon whose story has recently changed in a way that makes the whole picture sharper and stranger and somehow more moving. Among the smaller moons that circle close to the planet, there is one on a curiously stretched and tilted orbit. Its path is more eccentric than a moon on a calm, circular orbit should be, drawn out and inclined in a way that is hard to explain. For a long time, that odd orbit suggested it too might be a captured outsider, another body seized from elsewhere and never properly settled. It seemed, by its motion, to be another stranger. Recent study of that small moon has told a very different story, and it did so by reading the moon's light. As the moon gives off the faint warmth of infrared light, that light carries a kind of fingerprint of what lies on its surface. When that fingerprint was finally examined closely, it did not match the icy bodies of the distant belt at all. Instead, it looked much like the icy moons that circle the nearer giant worlds, the moons that formed in place. Its surface spoke of a local birth, not a distant one. That single reading changes the moon's identity completely. It means this small, oddly orbiting world is most likely not a captured stranger, but one of Neptune's own original moons, a survivor of the catastrophe. When the great backward orbiting moon was captured, and the original family was torn apart, this one small world was not destroyed. Instead of being shattered, it was violently kicked, flung into the strange, stretched orbit it still follows, and left there, alone. So the third largest of Neptune's moons appears to be a lone remnant of the planet's first family, thrown off its course by the intruder, but never quite broken. It carries the memory of the disaster in the very shape of its orbit. Every slow, tilted loop it makes around Neptune traces out the moment, long ago, when nearly everything around it was destroyed, and it alone endured. There is no drama in it now, only a quiet persistence, a small survivor keeping to its crooked path in the cold. The way its story was uncovered is itself worth admiring. For a long time, the moon's stretched, tilted orbit was the only real clue to its nature, and that clue pointed the wrong way, suggesting it was a captured outsider. It was only by reading the light from its surface, the faint infrared glow that carries the fingerprint of what a body is made of, that the truth came clear. The surface spoke of a local origin, of material like the icy moons born beside the nearer giants, not the material of the distant belt from which the great intruder came. A single careful reading of light overturned a long assumption, and turned a supposed stranger into a survivor. This is a small triumph of patience and technique, the kind that has reshaped so much of what we know about Neptune. No one traveled to the moon. No one landed on it or sampled it. Its true story was drawn out of the faint light it gives off, gathered across an enormous distance and read with great care. That we can determine the origin of a small moon at the edge of the sun's family simply by studying its glow is a quiet marvel in its own right, easy to overlook amid the larger drama of the moonpocalypse. And there is something fitting in the fact that the survivor kept its secret in plain sight, written in the light of its own surface, waiting for us to learn how to read it. The moon had been telling us what it was all along. We simply needed the right instruments and the right patience to hear it. Like so much about Neptune, the truth was there before we could see it, holding still in the cold until we were ready. It is a gentle thing to rest with, that idea of a single survivor. A world that was thought to be a stranger turns out to be the last of a lost family, carried through a catastrophe and left on an unusual road, still circling, still there. The violence is all in the deep past. What remains is only the slow, patient motion of a moon that outlasted its siblings, going quietly around and around the far blue planet. Beyond its moons, Neptune has surprised us in its own atmosphere, in a phenomenon that most of the other giant planets show openly, but that Neptune kept hidden for a remarkably long time. That phenomenon is the aurora, the soft glow that appears when charged particles from space stream down along a planet's magnetic field and strike the gases of its upper atmosphere. On many worlds, auroras are a familiar sight. On Neptune, they were almost impossible to find, and when they were finally caught, they were in the wrong place. To understand why they matter, it helps to remember what an aurora really is. A planet with a magnetic field is wrapped in an invisible set of field lines, like the grain running through a piece of wood. Charged particles, guided by those lines, are funneled down toward the places where the field dips into the atmosphere, and there they collide with the air and make it glow. The glow is a kind of map, a visible tracing of where the magnetic field meets the planet. It shows you, in light, how the planet's magnetism is arranged. The particles that make an aurora glow come from space, carried on the thin wind of charged matter that streams outward from the sun and gathered up from the planet's own surroundings. When those particles reach a planet with a magnetic field, they do not simply strike it everywhere at once. Instead, they are caught by the field and channeled along its invisible lines, funneled down toward the regions where the field plunges into the atmosphere. There, deep in the upper air, they slam into the gas and set it aglow. The color and the shape of that glow depend on what gas is present and on how the field is arranged, so that every planet's auroras carry the particular signature of its own atmosphere and its own magnetism. This is what makes auroras so valuable to those who study distant worlds. They are not merely beautiful. They are a way of seeing the invisible. A planet's magnetic field cannot be photographed directly. It is a structure of pure force, reaching out into space, utterly transparent. But where that field guides particles into the atmosphere, it lights a lamp, and by watching where the lamps appear, we can trace the otherwise unseen shape of the field. An aurora is a magnetic field made briefly visible, written in light across the top of a world. The tilt of Neptune's field is worth dwelling on, because it is so extreme. On a well-behaved planet, you can imagine the magnetic field as a simple bar magnet buried at the center, roughly lined up with the planet's spin, so that the magnetic poles sit near the geographic poles. Neptune is nothing like that. Its internal magnet is tipped far over from its spin axis, and it is shoved well off to one side, away from the planet's center. Imagine a bar magnet not standing upright at the heart of a globe, but lying at a steep slant and pushed toward the surface, and you begin to see how strange Neptune's arrangement is. The field that results is lopsided, uneven, far stronger in some regions than others. This crookedness is not just a curiosity. It is a clue about the deep interior, because a planet's magnetic field is generated within it by the motion of electrically conducting material far below. A field as tilted and off-center as Neptune's suggests that whatever is generating it is not a deep, orderly central core, but something shallower and stranger, a churning shell of unusual conducting matter closer to the surface. The wildness of the field points inward, toward an interior unlike the neat layered picture we might expect, and hints at the exotic states of matter we will meet deeper in this story. For now, it is enough to see that the misplaced auroras and the crooked field are two views of the same underlying strangeness. The auroras appear at the middle latitudes because the field guides particles there, and the field guides particles there because it is so steeply tilted and so far off-center. The glow we finally managed to detect is a faithful map of a genuinely unusual magnetism. Neptune is not lighting its auroras in the wrong place by any fault of its own. It is simply a world whose magnetism was never as tidy as we assumed, and the light merely tells the truth about it. On Neptune, the search for that light was long and frustrating. The planet clearly had a magnetic field, measured during the single close flyby, so it should have had auroras. Yet time after time, the glow could not be clearly found. The problem was partly one of sensitivity. Neptune is so distant and so faint that picking out a subtle auroral glow against the general light of the planet is extraordinarily difficult. It required instruments able to see in the infrared and able to isolate the specific fingerprint of a single telltale molecule before the auroras could finally be pinned down with confidence. The messenger that finally revealed them is a charged form of hydrogen, a fragile electrically active particle that forms in the upper atmosphere when auroral energy pours in, and that glows in a very particular way in infrared light. It appears where auroras are active. It shines in a color that careful instruments can single out, and its presence is a near certain sign that the aurora is real. Hunting for the glow of that one molecule, rather than for a vague brightening, would eventually be the key that unlocked Neptune's hidden light. But to appreciate why the discovery was so startling, it helps first to remember exactly what we expected an aurora to look like, and where. On the nearest giant worlds, auroras are almost constant, bright and steady features near the poles. On Earth, too, the auroras cluster near the north and south, because our magnetic field is roughly aligned with our spin, dipping down toward the atmosphere near the geographic poles. This is what we have come to expect. Auroras belong to the far north and the far south. They are a phenomenon of the poles, and that expectation is built deep into how we picture them. Neptune broke that expectation twice over. First, it simply refused to show its auroras at all for a very long time. They were suspected and searched for and not clearly found, decade after decade. It was only with a new generation of instruments, sensitive to infrared light, that the auroras were finally detected. The way they were found was itself elegant. Rather than looking for a general glow, astronomers picked out the specific signature of a particular molecule, a charged form of hydrogen that lights up distinctly when an aurora is present. Finding that molecule's glow in Neptune's upper atmosphere was, at last, the clear detection that had eluded everyone for so long. The second surprise was where the auroras appeared. On Neptune, they do not cluster at the poles. They glow far from the poles, down toward the middle latitudes of the planet, in the broad zone between the equator and the poles. To picture how strange that is, imagine the northern lights of Earth glowing not over the Arctic, but over the tropics, over the warm middle band of the world. That is roughly what Neptune does. Its auroral light appears where, on any ordinary planet, there should be none. The reason lies in Neptune's strangely tilted magnetic field, which is one of the most lopsided in the entire Sun's family. On most planets, the magnetic axis runs fairly close to the spin axis, so the magnetic poles sit near the geographic poles. Neptune's magnetic axis is tipped far over, by roughly 47 degrees, nearly halfway to a right angle from its spin. And the field is not even centered on the planet. It is offset, shifted well away from the middle of Neptune, as if the magnet inside had been pushed off to one side and turned on a slant. With the magnetism arranged so crookedly, the places where the field dips into the atmosphere are thrown far from the poles, out toward the middle latitudes. And so that is where the auroral glow appears, in the odd off-center places that the tilted field dictates. The light is not misbehaving. It is faithfully tracing a magnetic field that is itself deeply strange. The auroras are in the wrong place only by the standards of a tidy planet, and Neptune, as we keep learning, is not a tidy planet. There is one more reason the auroras were so hard to find, and it turns out to be tangled up with yet another surprise about Neptune. The auroras are faint, fainter than they should be, and their faintness is connected to a slow and quiet change happening in the planet's upper atmosphere. To see why the lights were dimmed, we have to look at the temperature of Neptune's outer air and at a cooling that no one saw coming and that no one can yet explain. When that single spacecraft swept past Neptune long ago, among the many things it measured was the temperature of the planet's upper atmosphere, the high, thin, outermost layer of air far above the clouds. That measurement became a baseline, a reading of how warm the top of Neptune's atmosphere was at one particular moment. Years later, when modern instruments measured the same layer again from a distance, they found something that no one had predicted. The upper atmosphere had grown dramatically colder. The size of the change is striking. The temperature of that outer layer appears to have dropped by several hundred degrees over the span between the early close measurement and the modern ones, a decline unfolding across only a few decades. Averaged out, it amounts to a loss of roughly 10 degrees each year, year after year, a steady and substantial cooling of the top of the planet's atmosphere. For a world we tended to think of as slow and unchanging, that is a surprisingly rapid shift. To understand why this is so puzzling, it helps to think about where a planet's warmth comes from and where it goes. A world like Neptune holds heat from two sources. A little comes from the distant sun, though at that range it is only a trickle. More comes from within, from the planet's own slow release of energy left over from its formation, and from the gentle settling of its interior. That inner warmth flows outward, up through the atmosphere, and eventually radiates away into space. The temperature of any given layer of the atmosphere is a balance, a steady negotiation between the heat arriving and the heat escaping. For the balance in the upper atmosphere to shift so far, so fast, something in that negotiation must have changed. Perhaps less energy is reaching the outer layer than before. Perhaps the outer layer has found some new way to shed its heat more quickly. Perhaps the change is tied to Neptune's long, slow seasons, the drawn-out shift of sunlight across the planet as it makes its century-plus journey around the sun. Perhaps it is connected to changes in the high hazes, or to some rhythm in the planet's own internal activity. Each of these is a reasonable thought, and none of them has yet been shown to be the answer. There is even a chance that the cooling is not a steady, one-way decline at all, but part of some slow cycle we have simply not watched long enough to recognize. Our measurements of Neptune's upper atmosphere are few, scattered across the decades, taken whenever a rare opportunity allowed. It may be that the planet's outer air rises and falls in temperature over long spans, and that we have happened to catch it during a falling stretch, mistaking one arm of a slow swing for a permanent trend. We simply do not have enough observations, spread across enough time, to know for certain. The honest answer remains that we are watching a change we did not predict and cannot yet explain. What makes it all the more striking is the sheer distance across which we are noticing it. We are detecting a temperature change of hundreds of degrees in the thin outer air of a planet so far away that we have reached it only once, using instruments here near the Earth and in orbit around it. To sense the slow cooling of the outermost skin of a world at the edge of the Sun's family, across the whole width of the planetary system, is a quiet marvel of patient observation. The mystery is real, but so is the remarkable fact that we can perceive it at all. It is worth being careful here about what the cooling does and does not mean. It would be easy to hear that a planet's atmosphere is cooling and imagine the whole world growing colder, the storms stilling, the planet slowly freezing further into silence. That is not what is happening. The cooling is confined to the high, thin outer atmosphere, the tenuous uppermost skin of the air, far above the clouds. That region holds very little substance, so its temperature can swing dramatically without much affecting the immense, dense atmosphere below. The deep weather layers, where the great winds blow and the dark storms turn, carry on much as before. Think of it as a change in the outermost breath of the planet, not in its body. The upper atmosphere is a delicate boundary region, where the planet's air thins away toward the emptiness of space. Such boundary layers are sensitive things, easily stirred by small changes in the energy reaching them, whether from the distant sun, from the planet's magnetic environment, or from waves rising up out of the deeper atmosphere. A relatively modest shift in any of these could cool that thin outer layer substantially, while leaving the great bulk of the atmosphere almost untouched. This is why the cooling can be so dramatic in degree and yet so limited in reach. Hundreds of degrees of change in a region that holds almost no heat to begin with is not the same as hundreds of degrees of change in the dense layers below. The planet as a whole is not undergoing some great transformation. It is the fine outer edge of its atmosphere that has cooled, quietly and unexpectedly, and it is there, in that thin, high layer, that the auroras dimmed and hid themselves away for so long. The cooling also quietly overturns one of our oldest assumptions about the distant planets, the assumption that they are, in effect, finished. It is easy to imagine the outer worlds as frozen and static, so cold and so far from the sun that nothing meaningful could still be happening to them. We picture them as museum pieces, preserved and unchanging in the dark. Neptune's cooling atmosphere says otherwise. Here is a world at the very edge of the Sun's family, changing measurably within the span of a few decades, shedding heat from its outer air fast enough for us to notice across the whole width of the planetary system. That is a humbling correction. The distant planets are not fixed and done. They are living worlds in the fullest sense, with weather, with cycles, with slow changes we are only beginning to track. Neptune's storms rise and fade. Its outer atmosphere warms and cools. Its seasons turn across more than a century, so slowly that we have watched only a fraction of a single one. To study it even briefly is to catch a world in motion, not a world at rest, and to be reminded that everything in the sky is, on some timescale, changing. There is a certain wonder in simply being able to witness such a change at all. We will very likely not learn in our lifetimes exactly why Neptune's upper atmosphere is cooling. The planet is too far, our visits too few, our record too short. But we can see that it is happening, and we can hold the question open, and there is no distress in that. An unanswered question about a distant world is not a burden. It is an invitation, a sign that there is still more to learn, and that the universe has not yet run out of quiet surprises to offer those who keep watching. And so the cooling takes its place beside all the other gentle corrections in this story, one more way that the real Neptune has turned out to be stranger and more alive than the tidy old picture allowed. The honest truth is that no one knows why it is happening. Nothing in our understanding of Neptune clearly predicts that its upper atmosphere should cool so quickly. There are ideas, of course. The cooling might be tied to the planet's long seasons, or to changes in its high hazes, or to some slow cycle in how the atmosphere sheds and gains heat. But none of these has been confirmed, and the cooling remains one of Neptune's most genuine open puzzles, a plain fact in search of an explanation. This cooling helps solve the mystery of the missing auroras. A colder upper atmosphere glows more faintly. The very layer where the auroral light is produced has been growing dimmer as it cools, turning down the brightness of the glow that astronomers had spent so long trying to detect. In a sense, Neptune was hiding its auroras behind its own falling temperature, dimming the lamp just as we were learning how to look for it. The faintness that made the auroras so elusive and the cooling of the outer air are two faces of the same quiet change. It is important to be clear about which part of the planet is cooling. This is a change in the high, thin outer atmosphere, the tenuous top of the air where there is very little pressure and very little substance. It is not the deep cloud layers where most of the planet's weather lives and where the great winds blow. Those deeper layers have not shown the same dramatic drop. It is the delicate, rarefied top of the atmosphere that has been shedding heat, the outermost skin of the world, far above the clouds. Still, there is something quietly remarkable in it. We tend to imagine the distant planets as fixed and finished, worlds so cold and far that nothing much happens to them anymore. Neptune says otherwise. Even now, even at the edge of everything, the planet is changing in ways we did not expect and cannot yet account for. Its outer air is growing colder year by year, for reasons that remain entirely open, and we are watching it happen from across the whole width of the planetary system. That is a strange kind of privilege, to witness a slow change on a world so far away that we have visited it only once. We cannot go and see why the cooling is happening. We can only watch and measure and wonder and add it to the growing list of things about Neptune that do not fit the old, simple picture. The planet turns in the dark, quietly losing heat from its outermost layer, and keeps its reasons to itself. And the deeper we look, the stranger the planet becomes. For all these surprises, at the color, in the moons, in the auroras, in the cooling air, sit above what may be the most surprising discovery of all. It concerns not the surface or the atmosphere, but the very substance of the planet, what Neptune is actually made of, deep down. And that discovery calls into question the name we have used for this world for as long as anyone can remember. For a very long time, Neptune and its neighbor have carried a particular name. We have called them the ice giants, to set them apart from the two larger worlds farther in, which we call the gas giants. The two names were meant to mark a real difference. The gas giants are enormous balls, dominated by hydrogen and helium. The ice giants were understood to be smaller and to hide interiors dominated by icy materials, by water and methane and ammonia beneath their own hydrogen and helium skies. It is a tidy division, and it has shaped how we think about these planets for decades. The names themselves tell a story about how our understanding grew. When the outer planets were first sorted into families, the great inner giants and the smaller outer ones seemed clearly different, and the word ice was chosen to capture the belief that the outer two were built largely of frozen materials. But the word ice, in this context, never meant quite what it means on a winter morning. To those who study planets, the ices are simply the substances that freeze at moderately low temperatures, chiefly water, methane, and ammonia, whether or not they are actually frozen inside the planet. Much of the ice inside an ice giant is not cold, hard ice at all, but hot, dense, fluid material under enormous pressure. The name was always a little misleading, even before the recent findings deepened the confusion. The new picture complicates it further by suggesting there is far more rock mixed in than the name allows. The clue, again, comes from careful study of the planet's outer envelope, the great mass of material above the deep interior. If that envelope were mostly hydrogen, helium, and ices, it would have certain measurable properties, a certain density and behavior. What the analysis finds instead points to a heavier, more mineral-laden mixture, an envelope salted through with the elements that make up stone. The planet appears to be carrying a great deal of rock high up, not just locked away in some small central core. This matters because it changes the very recipe of the world. A clean ice giant would be a fairly simple thing, a rocky heart wrapped in ices, wrapped in gas, in neat concentric shells. A rock-rich world is messier and more interesting. It suggests that as the planet gathered itself together from the material around the young sun, it swept up not just gas and ice, but a substantial helping of solid, rocky bodies, and that this rocky material never fully settled out, but remained mixed through much of the planet. The planet we are describing is less a tidy, layered sphere, and more a genuine blend, rock and ice and gas folded together. If the two outer giants differ in this blend, with one carrying more rock and the other more ice, then their differences run deeper than their similar sizes suggest. They may have formed in slightly different places, or at slightly different times, or gathered their material in slightly different ways. The habit of speaking of them as twins, born together and alike in all the ways that matter, may have been quietly smoothing over a real distinction. They are more like siblings with different temperaments than identical twins, shaped by subtly different beginnings into subtly different worlds. The reclassification, if it holds, would ripple outward beyond just these two planets. The categories we use to sort the worlds are not only labels. They shape how we think, what we expect, and how we group planets around other stars. If the outer giants of our own system are rock-rich rather than ice-dominated, then the whole family of similar worlds across the galaxy may need to be reconsidered in the same light. A great many distant planets have been imagined as ice-rich worlds simply because they resemble Neptune and its neighbor in size. If those two nearby examples are heavier with rock than we thought, our picture of that entire distant population may shift with them. This is the quiet power of studying the worlds we can reach. Neptune and its neighbor are the only planets of their kind that we can examine at anything like close range. Everything we learn about them becomes a template, a reference against which the countless more distant worlds are measured. A change in our understanding of these two ripples out to shape our understanding of thousands we can barely see. The rock hidden inside Neptune is not just a fact about Neptune. It is a correction that reaches across the galaxy. And it fits a pattern that runs through this whole account of the planet. Again and again, the tidy story has given way to a messier, richer truth. The bland blue twin became a pale and active world. The orderly moons became the survivors of a catastrophe. The polar auroras became a middle-latitude glow. And now the clean ice giant becomes a genuinely mixed world, heavy with rock, resisting the neat name we gave it. Neptune, it seems, has never been as simple as we wished it to be. It is a strange feeling to have a name you have used all your life come loose from the thing it names. For as long as most of us have known these planets, they have been the ice giants, and the phrase carried a whole picture with it. To learn that the picture may be wrong, that these worlds are heavy with rock, and perhaps deserve a different name entirely, is a small unsettling of something that felt fixed. And it is a fitting turn in Neptune's story, a planet that keeps declining the tidy categories we make for it. Recent work suggests that the name may be misleading, and that Neptune in particular may be far richer in rock than the label ever allowed. The clue comes from careful new analysis of the planet's outer layers, the envelope of material that sits above the deep interior. That envelope was long assumed to be a fairly clean mix of hydrogen, helium, and ices. The new analysis indicates something different. The envelope appears to be strongly enriched in rocky material, in the heavy mineral-forming elements that make up stone, far more than the simple ice giant picture would predict. By this reading, Neptune is not mostly ice at all. Its bulk appears to be a bit more than half rock, with the remainder divided between ices and gas. Its neighbor comes out slightly less rocky and a little more ice-rich by comparison. But both of them, on this account, carry far more rock than the name ice giant suggests. The picture that emerges is not of clean, frozen worlds, but of genuinely mixed planets, made of rock and ice and gas together, in proportions we are only now beginning to pin down. That difference between the two worlds matters, even though we so often speak of them as near twins. If Neptune is more rocky and its neighbor more icy, then the two planets were probably not built in quite the same way. They likely gathered their material a little differently, or in slightly different places, or at slightly different times, so that one ended up with a greater share of stone, and the other with a greater share of ice. The old habit of treating them as a matched pair may have been hiding a real and telling difference in their histories. Some researchers have gone so far as to argue that the pair should be reclassified, thought of less as ice giants and more as a distinct category of their own, a kind of intermediate world defined by its heavy load of rock. The exact choice of name is less important than the shift in understanding behind it. Whatever we decide to call them, these are not the clean balls of gas and ice we long imagined. They are mixed worlds, and Neptune especially seems to be a planet with a great deal of rock woven all through it. Now, it is worth being honest about how uncertain the interior of any planet must remain. We cannot see inside Neptune. No instrument has ever looked beneath its clouds and reported back on what lies there. Everything we say about the interior is reconstructed indirectly, from the planet's size and mass, from the way its gravity is distributed, and from how it responds to its own rapid spin. These are real clues, but they are clues read from the outside, and they leave genuine room for revision. The rock-rich picture is a strong and careful inference, but it is an inference all the same. Nor is it yet clear exactly how the rock, ice, and gas inside Neptune are arranged. They might be thoroughly mixed together, blended all through the interior. They might have settled into distinct layers, rock beneath ice, beneath gas. Or the truth might lie somewhere in between, with regions that grade slowly from one into another. We do not know, and that uncertainty is itself part of the story, a reminder of how much of this world is still hidden from us. How the interior is layered may connect to that strangely tilted, off-center magnetic field. A magnetic field generated in a shell of unusual mixed material, rather than deep in a tidy central core, could naturally come out lopsided and offset, exactly as Neptune's field appears to be. The crooked magnetism that throws the auroras to the middle latitudes may be a direct sign of an interior that is nothing like the neat, layered picture we once drew. The strangeness on the outside may be a message from the strangeness within. And when we try to imagine the conditions in that interior, the strangeness only deepens. Deep inside Neptune, the pressures and temperatures rise to values far beyond anything at the Earth's surface, extreme enough that ordinary materials stop behaving in ordinary ways. Down there, in the crushing dark, matter itself is expected to take on forms we barely understand, forms that may hold the key to the planet's crooked magnetism, and that we cannot yet make or study anywhere but in the deep interiors of distant worlds. Below the atmosphere of Neptune, as you sink toward the center, the weight of the world above you grows without pause. The pressure climbs to values almost impossible to picture, and the temperature rises along with it. The interior of Neptune is a place of conditions so extreme that the familiar rules of solid, liquid, and gas begin to lose their meaning. Down there, matter is squeezed and heated into states that have no everyday counterpart, and the deep interior becomes a domain of strange and half-understood chemistry. Take water, the most ordinary substance we know. At the surface of the Earth, water is a gentle thing, liquid in our rivers, solid in our ice, vapor in our clouds. Deep inside Neptune, under enormous pressure and heat, water is thought to enter states unlike any of these. In one such state, it behaves partly like a solid and partly like a liquid at once, its structure locked into a rigid lattice, while, within that lattice, pieces of it flow freely and carry electric current. It is neither ice nor water as we know them, but something else, a hot, dense, conducting form of water that could only exist under such crushing conditions. It is worth pausing to feel how alien these conditions are. We think of water as one of the most familiar substances in existence, the stuff of oceans and rain, and the glass on a bedside table. But everything we know about water comes from the narrow range of pressures and temperatures found near the surface of the Earth. Push water hard enough and heat it enough, and it stops behaving in any way we would recognize. The neat categories of solid, liquid, and gas begin to blur and give way to other states entirely, states that have no place in ordinary life and can only be reached in the crushing interiors of worlds or in the briefest, most extreme experiments. Deep inside Neptune, water may spend its existence in one of these strange states, having forgotten entirely how to be the water we know. The same is true of the other materials down there. Under enough pressure, the familiar rules that separate one kind of substance from another begin to soften. Gases are squeezed until they behave like liquids or metals. Solids are compressed into forms with properties they never show at the surface. Mixtures that would never combine in ordinary conditions are forced together into new arrangements. The deep interior of Neptune is less a place of ordinary rock and water and gas than a laboratory of exotic matter, running experiments that no one designed, at pressures and temperatures we can barely approach. This is why the interior is such a rich frontier, and such a humbling one. We can reason about it. We can build models and run calculations and stage tiny, fleeting experiments that reproduce a hint of those pressures for a fraction of a second. But we cannot go there. We cannot drop an instrument into Neptune and watch what water does at its heart. Everything we say about the deep interior is a careful inference, a best guess built from physics and from the planet's behavior as seen from outside. The center of Neptune is one of the least accessible places we know of, sealed away beneath thousands of miles of atmosphere, and it keeps its secrets almost perfectly. And yet those hidden secrets may be writing themselves, faintly, across the face the planet shows us. The strange states of matter deep inside are not merely curiosities locked away in the dark. If they truly exist, they shape the planet's magnetic field, and that field reaches all the way out into space, where we can measure its crooked, off-center form. The exotic matter in the depths and the lopsided magnetism at the surface may be two ends of a single thread. By studying the field from afar, we may be reading, indirectly, the behavior of matter in a place we can never visit. The idea of diamonds forming in the depths deserves a gentle second look, because it is one of the more striking images in all of planetary science, and it flows naturally from this strange chemistry. Deep inside these worlds, the pressure can grow great enough to break apart the molecules that contain carbon, freeing the carbon to gather on its own. Under such crushing conditions, that carbon is expected to lock into the dense, ordered form we know at the surface as diamond. Once formed, these dense grains would be heavier than the material around them, and so, over immense stretches of time, they would slowly sink, drifting down through the interior toward the center of the planet. It is an almost dreamlike picture, a slow and silent fall of diamond-like material through the dark heart of a distant world. There is no storm to it, no drama, only an unimaginably patient settling, grain by grain, over spans of time that dwarf the age of everything we know. If it is real, and the physics suggests it may well be, then Neptune carries within it a hidden weather utterly unlike anything at its surface, a deep and gentle rain of crystallized carbon that has been falling, perhaps, since the planet was young. We cannot confirm it directly, of course. Like so much about the interior, it lives in the domain of careful reasoning and delicate experiment rather than direct observation. But it captures something essential about Neptune's depths. Down there, the ordinary becomes extraordinary. Carbon becomes crystal. Water forgets how to be water. And matter arranges itself into forms that exist nowhere in our daily experience, sealed away in a place we can model and imagine, but never reach. The interior of Neptune is a frontier not of distance but of conditions, a strangeness measured not in miles but in pressure and heat. A layer of such conducting, churning material is exactly the kind of thing that can generate a magnetic field. When electrically conducting matter moves and swirls, it can act as a natural dynamo, spinning a magnetic field into being. And a field produced in a shell of this exotic matter, rather than in a deep and orderly core, would naturally tend to come out tilted and off-center, just as Neptune's field does. The strangely lopsided magnetism we measure from outside may be the direct signature of these strange states of matter moving in the planet's depths. The strangeness does not stop with water. Carbon and hydrogen, deep inside these worlds, are expected to be squeezed into unusual crystalline forms of their own. In some descriptions, the intense pressure forces carbon to separate out from the material around it, gathering into dense crystalline grains. This is the origin of a long-standing and rather beautiful idea that deep within these planets there may fall a slow, quiet rain of diamond-like material, sinking through the interior over unimaginable spans of time. It is a striking image, a hidden weather of crystallized carbon, drifting down in the dark. Under certain conditions, the carbon is predicted to lock into a particularly unusual arrangement, a lattice that lets electricity flow in one direction but not the other. It is a lopsided electrical behavior, a kind of one-way street for current buried in the heart of the planet. Such one-directional behavior is deeply strange to picture. In the ordinary materials of everyday life, electricity that can flow one way can generally flow the other way just as well. A material that permits current in a single direction and resists it in the reverse is doing something unusual, something that arises only from a very particular arrangement of its atoms. That the crushing pressure inside Neptune might force carbon into exactly such an arrangement is a remarkable prediction, and if it holds, it would be one more ingredient in the recipe that produces the planet's crooked, off-center field. It is worth stepping back to see how all these deep interior ideas fit together. A shell of hot, conducting water that can carry current. Carbon squeezed into dense, crystalline grains that slowly rain downward. Unusual lattices that pass electricity in only one direction. None of these belongs to the tidy, layered picture of a simple planet. Together, they sketch an interior that is genuinely exotic, a churning, mixed, electrically active region unlike anything in the inner worlds. And that exotic interior offers a natural home for the strange magnetism we measure from outside. The connection runs both ways, which is what makes it so valuable. The lopsided field we can measure from afar becomes a clue to the exotic matter we cannot reach. And the exotic matter, worked out through physics and experiment, becomes an explanation for the field. The outside and the inside speak to each other, each helping to make sense of the other. In this way, a magnetic field traced by faint auroras at the middle latitudes becomes a window, however clouded, into the deepest and least reachable place in the whole planet. Such an arrangement, if it truly exists deep inside Neptune, could feed and shape the planet's magnetic field in its own strange way, adding yet another odd ingredient to the recipe that produces the crooked magnetism we see from afar. It is important to hold all of this gently, because much of it remains at the very edge of what we can test. These exotic states of matter are studied through careful reasoning, through the mathematics of how materials behave under extreme conditions, and through delicate experiments that briefly reproduce a hint of such pressures here on Earth. But we have never sampled the interior of Neptune, and we cannot. The precise states of matter deep inside the planet, and the exact way they shape the field we measure from outside, remain among the harder, unanswered questions in the study of planets. And there is something quietly wonderful in that uncertainty. Deep inside a world we have visited only once, in conditions we can barely reproduce, matter may be doing things we have only begun to imagine, arranging itself into forms that exist nowhere in our ordinary experience. Neptune carries in its hidden depths a chemistry we can model but not yet visit, a strangeness sealed away beneath thousands of miles of atmosphere. It is a reminder that even the substance of a planet can be a frontier. For all its remoteness, though, Neptune is not merely a distant curiosity, a strange world worth studying only for its own sake. There is a deeper reason it has moved toward the center of attention, a reason that reaches far beyond the edge of our own planetary family and out among the countless worlds that circle other stars. It turns out that planets like Neptune may be among the most common in the entire universe, and that to understand this one faint blue point is to understand a great many worlds we will never see. It would be easy to think of Neptune as a remote and minor thing, a faint world at the far edge of our system, interesting perhaps, but hardly central to the larger story of planets. The truth is almost the opposite. Among all the planets we have found circling other stars, worlds of Neptune's size and mass appear to be among the most common of all. The faint blue point at the edge of our own family may be one of our closest examples of the ordinary planet of the universe. This is a genuinely surprising turn when you sit with it. For most of our history, we naturally assumed that our own arrangement of planets was the ordinary one, that the rocky inner worlds and the great gas giants represented the normal pattern of things. As we began to find planets around other stars, that assumption slowly came apart. The worlds we kept finding, again and again, were not close matches to any of our familiar planets. They clustered, instead, in that in-between range, larger than the Earth and smaller than the giants, the range that Neptune and its neighbor occupy. It began to look as though our own system, with its particular set of worlds, might be the unusual one, and that the true, ordinary planet was something more like Neptune. The strange part is that our own system has these mid-sized worlds only far out in the cold, as the two outermost giants. Around other stars, planets of this size are often found much closer in, orbiting near their suns, warm and swift. We have nothing like that here. Our inner system holds only small, rocky worlds, and our mid-sized worlds are exiled to the frozen edge. Why our system turned out this way, lacking the most common kind of planet in the warm inner regions, is itself an open question. But it means that when we want to study the ordinary planet up close, we must look outward, to the cold and distant giants, because they are the only nearby examples we have. And this is where the reinterpretation of Neptune's makeup becomes so valuable. If planets of this size carry a great deal of rock beneath their gassy envelopes, that helps explain a pattern seen among the distant worlds. Many planets of about this size appear to lose their thick atmospheres over long spans of time, stripped away by the radiation of their nearby stars, or lost through slow escape into space. When such a world sheds its gas, what remains is its heavy, rocky bulk, a bare world somewhat larger than the Earth. Worlds of exactly this kind are common around other stars, a whole population of stripped, rocky planets, and yet our own system has not a single one. Understanding what Neptune is made of may be part of understanding how those distant worlds are born, and why we lack them. So the picture comes full circle. The strange, active, rock-laden Neptune emerging from all this recent work is not a remote curiosity after all. It is a key, one of the few we can reach, to reading the most common planets in the universe. Every correction to our picture of this one world, the truer color, the broken moons, the misplaced light, the cooling air, the hidden rock, sharpens our ability to understand an immense population of worlds scattered across the galaxy, most of them far beyond any hope of a close look. To learn Neptune well is to learn something about planets almost everywhere. When astronomers survey the planets of other stars, they find that a very large share of them are intermediate in size, larger than the Earth but smaller than the great gas giants, sitting squarely in the size range of Neptune and its neighbor. This in-between size, neither small and rocky like the inner worlds, nor enormous like the largest giants, is one of the most abundant kinds of planet in the galaxy. It is strange to realize that our own system's only examples of this common type sit far out in the cold, where we so rarely look. Because these mid-sized worlds are so common elsewhere, understanding Neptune and its neighbor becomes a way of understanding a whole galaxy's worth of planets. They are our two nearby, reachable examples of a type of world that exists in enormous numbers around other stars, most of them far too distant ever to study in any detail. Whatever we can learn from the two we have close at hand, we can carry outward and use to make sense of the countless others we can only detect as faint shadows crossing distant suns. The rock-rich reinterpretation of Neptune feeds directly into this larger picture. If planets of this kind carry large amounts of rock beneath their gas, that helps explain something we see among the distant worlds. Many planets of about this size seem to lose their thick atmospheres over long spans of time, and when they do, they may be left as bare, rocky worlds somewhat larger than the Earth. Such stripped, rocky worlds are common around other stars, and yet, tellingly, our own system has none of them. Understanding what Neptune is made of may help explain how those worlds are born and why we lack them. So the strange, active, rock-laden Neptune emerging from all this recent work is far more than a local oddity. It is a key to reading the most common planets in the universe. Every correction to our picture of this one world, the truer color, the broken moons, the misplaced auroras, the cooling air, the hidden rock, sharpens our ability to understand an immense population of worlds scattered across the galaxy. To learn Neptune well is to learn something about planets almost everywhere. There is a further reason these mid-sized worlds matter so much to us, and it touches on the oldest questions we ask about the sky. Among the great goals of studying planets is to understand which of them might, in some form, be hospitable, and how planetary atmospheres are gained, held, and lost. Worlds of Neptune's size sit right at the heart of that question. Whether a planet keeps a thick atmosphere or is stripped down to bare rock depends on its makeup, its distance from its star, and the slow processes that act on it over ages. By understanding how Neptune came to be what it is, we learn to read those processes and to guess at the histories of worlds we will never visit. Every distant planet we detect is little more than a shadow and a set of numbers, a faint dimming of a star, a slight tug on its motion, a whisper of light. To turn those whispers into worlds, we need nearby examples we can study in depth, planets whose makeup and behavior we can examine closely and then use to interpret the faint signals from afar. Neptune is one of our few such touchstones for the most common kind of world in the galaxy. It is a reference world, a key we hold in our own system for unlocking countless others beyond it. So the far blue point that we once treated as an afterthought turns out to sit near the center of some of the largest questions in the study of planets. It is not the strangest world for its own sake alone. It is a guide to the ordinary worlds of the universe, a nearby example of a distant multitude. And that lends a quiet weight to how little we have actually visited it. And yet, for all its importance, Neptune has been visited up close only once, and only in passing. That single brief flyby, long ago, still supplies a large share of what we know, and everything discovered since has come from an enormous distance. It is a little astonishing, when you sit with it, that our nearest example of the most common kind of planet in the universe has received exactly one short visit in all our history of exploration. So much has been learned from so little, and so much more waits to be learned. This is why many who study the planets now argue for a return, for a dedicated mission that would travel to Neptune and stay. Rather than sweeping past in a matter of days, such a spacecraft would settle into orbit and study the planet, its rings and its moons over years, rather than moments. It would be able to answer questions that the single flyby and our distant telescopes never can. Questions about the true makeup of the interior, the behavior of the tilted magnetic field, the nature of the auroras and the cooling, and the deep history written into the broken family of moons. Such a mission is often proposed, but has not yet been built, and the distances involved make it a patient undertaking. Because Neptune is so far away, even a mission approved and begun would take many long years to plan, to launch, and to make the enormous crossing to the outer dark. A journey to Neptune is measured in decades, from the first decision to the moment of arrival. Anyone who sends a spacecraft there is planting a tree whose shade they may wait a very long time to sit in. There is a particular kind of patience required for a mission to the outer worlds, a patience that spans careers and even generations. Those who might first imagine and design such a spacecraft may not be the same ones who guide it through its long crossing, and those may not be the ones who finally receive its discoveries when it arrives. A journey of decades asks people to begin something they may never see finished, to work toward a payoff that will fall to others. And yet, again and again, this is exactly what the exploration of the distant worlds has asked, and exactly what people have been willing to give. What such a mission could return would be worth the wait. An orbiter settling in around Neptune, staying for years rather than passing in days, could watch the great storms form and fade, trace the crooked magnetic field through a full turn of the planet, follow the auroras and the cooling of the outer air over time, and study the broken family of moons up close. It could test, at last, the rock-rich picture of the interior, and perhaps detect indirect signs of the exotic matter deep within. It could turn the single frozen frame of the old flyby into a moving picture, a true and patient portrait of the world. Until such a day comes, though, we will go on as we have, learning Neptune from afar, wringing new understanding from faint light and old data and ever sharper instruments. And there is no urgency in it, no need to hurry. The planet is not going anywhere. It has kept its slow orbit at the edge of everything for far longer than we have existed, and it will keep it for far longer still. Whatever we learn of it, and whenever we finally return, it will still be there, turning quietly in the cold. Perhaps that is the gentlest way to hold this whole story. Neptune is not a problem to be solved on any particular night, nor a world that demands our attention. It is simply there, far and patient and strange, slowly revealing itself to those who take the trouble to look. We are still in the early chapters of knowing it, and that is not a lack but a kind of gift, the promise that there is more still to come. Every generation that has looked closely at Neptune has found it different from what they were told, and there is little reason to think that will change. The planet will keep quietly rewriting itself in our understanding, one careful observation at a time, for as long as we are willing to keep looking. And each correction, rather than diminishing the world, has only made it richer, stranger, and more worth the looking. Until that day comes, our understanding will keep advancing the way it has lately, from afar, through ever sharper instruments, each new look capable of rewriting the picture once again. And that, perhaps, is the gentlest truth in all of this. Neptune is not a settled world at the end of a diagram, a planet fully known and safely filed away. It is a world we are still meeting, whose real nature has only recently begun to come into view, and which will keep surprising us long after tonight. There is a quiet comfort in that thought, in a world so far away and so patient with its secrets. It has no need of our attention. It has turned in the cold and the dark for far longer than we have existed, and it will keep turning long after this night is forgotten. Whatever we learn of it, and whenever we finally return, it will still be there, pale and strange and unhurried, at the edge of everything. And so we leave Neptune where it has always been, turning slowly in the cold and the dark, far paler and far stranger than we once believed, still keeping most of its secrets. There is no need to solve any of it tonight. Let the great distance be a comfort rather than a loneliness. Let your breathing slow, let your thoughts drift out past the last planet, out past the broken moons and the crooked light and the quiet rain of diamonds in the dark, and let them settle there, in the stillness at the edge of the sun's family. Sleep well, and good night.